How are you doing,
I'm
Maury? Thanks for
doing
joining me.
well, Thanks so much. Thanks for inviting us.
Oh, no problem. No problem. And we could just go ahead and jump right in. We chatted a while back, and then when we last chatted, you mentioned that processors, the compute accelerator boards, compute trays, they represent about 50% of total rack power, meaning that efficiency gains made there attack the bulk of the AI data center energy consumption problem. Can you explain why you think efficiently delivering power to the processor is the most important power problem in data centers?
Yeah, again, Ali, as I had mentioned earlier, the uh, the losses associated with powering the processors is really the bulk of the challenge with respect to getting the entire data center power utilization as high as possible. So it's absolutely a key element of addressing what is becoming more of a societal level concern about the enormous amounts of energy that these AI data centers are using these days.
Gotcha. And maybe we could talk about the magnitude, the impact of marginal efficiency improvements in data centers. What does that mean on a larger scale, especially as data center power consumption skyrockets?
Um, yeah, again, the focus for power engineers really needs to be looking at the complete chain. As you might know, there's
Yeah,
a big initiative to move the feeds to the racks from 48 volts to 800 volts DC.
yeah.
And that's, from our perspective, really running in the right direction, if I can say, in terms of reducing dramatically those I squared R losses in those cables. There's a lot of current passing through those, as you can imagine, with these racks eventually in a path to, well, certainly to hundreds of megawatts, and then eventually perhaps up to even higher. So,
Yeah.
starting from that 800 volt feed to the racks, it's then important, of course, minimize the number of DC-DC conversion stages, and then make sure that the losses and efficiency associated with each one of those stages is optimized to really attack this problem.
So you've described AI workload transients as brutal with near instantaneous swing from idle to full load. Can you expand on this and how does that impact the characteristics of power delivery systems for training and inferencing processors?
Sure, of course. So, yeah, the workloads in both training and inference processors, particularly training processors, can effectively move from a no load state to a full load, sort of in the vernacular of power engineers. So the power delivery system, the last stage data converters need to have very high transient bandwidth. There needs to be a hierarchy of energy storage, particularly decoupling capacitors, as
Mm,
close to the processor as possible to supply energy
yeah.
across those transient events to make sure that the voltage doesn't droop excessively. Um, the rest of the power delivery system needs to be there with sufficient ability and bandwidth to be able to, after that first level of hierarchy in terms of energy storage is depleted, the regulators need to come through rapidly to support the transient demand. And by doing so with adequate bandwidth, you can avoid the processor doing any kind of throttling, any kind of dynamic frequency or voltage scaling in order to effectively, wait for the power delivery system to catch up to these transients. So it needs to be very, very rapid so that the performance of these processors can be maximized.
Mm, okay. And I know that Vicor doesn't focus only on the vertical power delivery solution or the VPD solution. There's also a thought process behind delivering power to the VPD modules. So, and this is surrounded by the factorized power architecture. So, can you describe that, the FPA that takes the 48 volts directly to the load? And what's the penalty for stepping down to 6 volts or 2 volts prior to the final stage buck regulators?
Right. So just a brief review of factorized power architecture. It's something that
Yeah.
Vicor has advocated, has innovated around for many years. The difference, essentially, FPA is a disaggregation of the regulation stage from what we call the transformation stage.
Hmm.
The VPD modules receive the 48 volts from stable 48 volts from the regulator. So this factorized power architecture does regulation and then transformation. Competitive solutions do the opposite. They do transformation or fixed ratio step down, and then whether to 6 or 2 volts, and I come back to that, and then regulation. So we've FPI kind of turns that back around. As I said, the vertical power delivery modules receive the 48 volts, transform that using what we refer to as a K factor. So you can imagine that if there's 48 volts coming in, if the K factor is 48, then the voltage is divided by 48, and the current is multiplied by 48. And so you can think of that as current gain, maybe an easier way to think about that. And so as a consequence, you've brought 48 right to the VPD modules, effectively right to the point of load. And by so doing, at that higher voltage, really independent of what the resistance is across the printed circuit board, because the regulator is going to be somewhere that's not exactly adjacent to the processor. There's going to be some distance there, and therefore some resistance through those conduction paths. And so 48 volts really, as much as possible, and it's still a safe voltage. There's no safety concerns. It's something that's been used in automotive platforms and other platforms for a number of years. And so, again, the 48 volt minimizes the losses across that conduction path. By contrast, if you move to 6 volts, as some solutions have done, then you're talking about a much higher level of current across that last stage, and of course that increases the thermal losses tremendously. And then 2 volts at the point of load is even worse. It's given that 2 volts is only effectively 2x the final. Well, it might be say 4x if you're delivering half a volt, right? So there's a very little bit, only a very small amount of step down. In our case, it would be transformation. In their case, it would be in other solutions, it would be regulation. And so, we see 48 volts again running in the right direction to minimize power, just like the 800 transition from 48 volts at the whip or the cable level going into the racks is doing a similar thing. So that's kind of our perspective on this. We have a unique solution that we think really addresses the most pressing concern with respect to powering these processors.
So I've heard that adding a 2-volt intermediate power bus segment instead of going directly from 48 volts to the VPD module will cause IVR solutions to struggle to scale up beyond a few hundred amps of thermal design current. Do you feel this is the case? That's what you basically just explained.
Absolutely. And, some of the consequences of using that lower voltage with the higher thermal losses is you're creating, additional thermal stress on the package. So if these IVRs are mounted in the package, again, you're kind of multiplying the problem with respect to the heat that needs to be drawn out of the package. There's a number of other issues from my perspective with embedding regulators within the package. The substrate of that package assembly needs to be customized. If there's any failure of these lower output current IVRs, then you would have to scrap presumably the whole package assembly with the processor, particularly if that failure occurs over time. There's no opportunity for rework or any kind of repair, and so you really run into trouble there. And there's a number of other issues, Ellie, that we can discuss if you'd like.
Yeah. Well, maybe we could talk about the reasoning behind going down to 2 volts. I've been told that going from 2 volts to the core offers better efficiency than using higher input voltages like 6 volts, 12 volts, or 48 volts to the core. And this is the thought process for many IVR solutions, for example. There's a balancing act between the input voltage and efficiency, and you don't want to sacrifice efficiency gains in that last mile of delivery, because as we were speaking about earlier, most important power problem in data centers, you don't want to sacrifice that for the sake of input voltage. So what are your thoughts there?
Yeah, for multi-phase voltage regulators, you do need to avoid a large step down because of the way those regulators are controlled, which is through a pulse width modulation technique. You start to have a very low repetition rate of those pulses as you have a higher step-down ratio. So I think what you're referring to is that when you have a very small step-down ratio, in this case, either 2 to 1 or 4 to 1, from 2 volts down to half a volt. For that topology, for the multi-phase approach, you are going to have better efficiency. In our solution, that's not an issue. As I said, the current multiplier can deal with factors of 48 or higher with no loss of efficiency. I'd like to make another point as well. The thermal dissipation, the heat generated by those I2R losses really dominates. Power converters have relatively high efficiencies in the, say, 90 plus range continuously, average average efficiency. So there are relatively small gains to be made with respect to these thermal losses due to the efficiency of the converters themselves. The real win is attacking those the losses across the conduction losses, the I2R losses, and that generates the bulk of the dissipation. So yes, I can understand how if you were to use multi-phase, you want to have that small conversion ratio.
Yeah.
But there are alternatives to that, as we've talked about, and furthermore, you're really it's sort of pound smart. Whatever the expression is, pounds and pennies, right? So you're making sort of a deal with the devil, if I can say it that way. You're driving up the efficiency of the converter, but you're then inducing all these other thermal losses across the conduction paths.
Thank you. And you were talking about earlier the most multi-phase. Most vendors use the multi-phase TLVR topology, but Vicor's is different. That they're used as a fixed ratio current multiplication, and maybe you could talk about the merits of this. I know that you described quite a bit already, but maybe we could talk about that a little bit more. The merits of that current multiplication in the power chain.
Yeah. Excuse me. One of the things I would mention there is that when you think about this regulation transformation architecture that is used by factorized power architecture, the current multiplier, the downstream current multiplier, which is the VPD module, inherits the regulation of the first stage voltage regulator. So it's coming in at a very tightly regulated 48. Then you're doing the voltage transformation, which is, you can think of it as current multiplication, which is fixed ratio, right? So that fixed ratio, as I said, can be whatever's needed by the power domain rail that it's servicing, if I can say that. So you can sort of dial in, and in fact, these current multipliers, as well as the voltage regulators, is a standard product family with a variety of output currents, of K factors. So there's the opportunity to use these in a VPD configuration without any customization of the substrate, without any concerns about rework because they're on the back of the board, without any concerns about displacing the capacitor array, the capacitor farm, the decoupling capacitor farm on the backside of the board, because the current density of the current multipliers is extremely high. And so you're kind of in a much better position, pretty much from all perspectives: lower heat, reworkability, repairability. You have no concerns about having to, very high efficiency, no concerns about having to even think about these step-down ratios to maximize multi-phase efficiency. So there's lots and lots of merits, and we're very committed and see this as the best path, again, running in the right direction in terms of reducing the losses that really dominate AI data center concerns with respect to power losses. So,
Thank you, Maury. I the capacitance multiplication via the current multiplier DC turns ratio, or K factor. That Vicor has a lot of very specific terms, but I wanted you to kind of explain that in a little bit more detail. Can you explain how the transformer turns ratio ends up multiplying the effective power chain capacitance? And then this is very relevant because, in AI accelerators where power delivery is dependent on those capacitor farms, as you were saying, that hierarchy of energy storage, describing earlier. So maybe you could talk
Yeah.
about that.
So the capacitance on the input side of the current multiplier is multiplied up by the square of the K factor. So there's a tremendous um, impact on that capacitance, and that appears on the output side of the
Yeah,
current multiplier. So it's a unique trait of current multiplication. It, as you said, really helps with respect to energy storage as close, again, closer to the processor. So now you're talking about on the on the output side of the
yeah,
VPD module. So you're getting within, a millimeter or so from the
yeah,
actual processor to the substrate and up through the multiple. There are actually tens of thousands of microvias in these substrates
yeah.
feeding up, and about half of those are power and ground up to the power and ground connections of the processor itself. So you're really getting this terrific attribute of current capacitance multiplication, to your point, adding to the reserves of energy available in the event of, or the frequent event of these workload transients. So it's tremendously beneficial with respect to dealing with these transients.
Gotcha. Thank you, Maury. So I got like two more questions and then you're off the hook. But maybe we could talk about that small ecosystem of IVR solutions, emerging, and these regulators that they could be attached to the bottom side of the accelerator PCB in a vertical power delivery configuration, but they can also be placed on the bottom surface of the package assembly substrate or embedded within it. And of course, as you were talking about earlier, it comes with its own challenges. But I was curious, what were your thoughts on this approach? And is Vicor watching this?
Yeah, I think we're watching it. I think that
Yeah,
conceptually it makes sense. I think in actual usage, I'm not going to go back and talk about some of the
yeah,
things that I
yeah,
covered, but I do think that, and to your point, the so far as we know, the output current levels of IVRs is quite low.
mhm,
So I think the fit there might be for auxiliary rails that don't demand as much as the core rail for these AI processors. So there's potentially a fit there. I think to your point, it's becoming evident that these solution providers are positioning it as being either something that can be done in traditional VPD in the back of the printed circuit board. It can be done on what people refer to as the LAN side of the
yeah,
PCB, or attached to the bottom of the substrate. One of the issues there, of course, is the height of those modules in
yeah,
order to be able to be compatible with the package assembly, and then the full embedding of those into the substrate.
yeah,
And one point I haven't made with that is that by taking the approach of embedding them into the substrate, every single substrate for every processor variant have to be customized. Furthermore, you're taking a passive substrate, which might have embedded, or very likely has embedded capacitive elements, but now you're introducing active electronics, active power electronics in the form of these regulators into the substrate. So it's a huge change in how people have thought about substrates, and so it would require a remarkable level of cooperation, not only with the end customer, the
yeah,
processor developer, but also the substrate maker, so that you can successfully customize every substrate that will be using this technology. So again, I think in concept, I think that it's got some merits. I think in practical application, there are some shortcomings that need to be addressed.
yeah. Gotcha. I remember you mentioned earlier that the vertical power delivery market in and of itself is still quite new. It's mostly been lateral up until now as well. But I I was just curious your thoughts, kind of, more forward looking there. And maybe you could talk about if you have any final thoughts, what's next for the roadmap. Um,
Yeah.
you know, uh, just anything that I might have missed, and I'm sure I did.
Sure. Yeah, I'd love to give a kind of a foreshadowing of something that I've been looking
Yeah,
into, and
yeah,
others at Vicor have as well, which is that the roadmap for these processors. So the major suppliers of the substrates
yeah,
used in these package assemblies are looking at much larger panels and transitioning to glass substrates, and looking at panels that are 200 millimeters by 200 millimeters,
yeah,
400 millimeters squared, 600 even, which is extraordinarily huge.
yeah,
And the thought process is that then you can take at the chiplet level rather than the package assembly level and construct processors with just enormous
Yeah.
compute performance. And you also experience a tremendous increase in compute density because the area required by chiplets is much smaller, surprisingly smaller than the
Mm.
area required by a package assembly. And so in the future, you're going to see these much larger panels that have a lot more compute resources, a lot more I/O. They'll have co-packaged optics. But my point
Yeah.
is that my key point is that in the era, which will be 2029 or so, of these
Yeah.
panel-sized processors, you have to use VPD. There's no alternative to that. There's absolutely no
Mm.
alternative to VPD.
Yeah.
And furthermore, you need to have solutions that have very high current density. And because of the concentration of energy in these panels, the idea of then having any kind of embedded voltage regulator that contributes to the thermal footprint of that panel is going to be unacceptable. So, there'll be much more stress on the liquid cooling, and when that time arrives, and there's a tremendous amount of R&D dollars going into panelized processors,
Yeah.
you're going to have to totally optimize the thermals. You're going to have to optimize efficiency of the entire path. So, at the gain of compute density, you're going to have some additional new thermal challenges, and we think that 48 volt factorized power architecture is the way to go and to attack that.
Thank you so much, Maury. I really appreciate your time. Thank you for taking out the time to speak to me. This is a very enlightening discussion. I have really appreciated it. I learned a lot myself. So
Great,
thank
Ali,
you.
it's been terrific speaking
I
with you
hope
this
I
morning.
asked the right questions. I do appreciate it. But the
One last word, Ali.
yeah,
This whole topic at the end there, this panelized processor thing, I think
yeah,
is extremely interesting. Number one, we're going to have some good things to show you, I think, in that domain. But I think
yeah,
that foreshadowing and the reality of that coming down the road forces a lot of these issues that we talked about much more to the forefront, and
yeah,
really sort of make some of the things that people are sort of dabbling with, like VPD and other things,
yeah.
it clarifies all those issues because you can't mess
Oh,
around. I mean, the amount of I did one study and it was it's like 30,000 amps or something like that. It's
oh,
unbelievable
okay.
level of current
Oh,
and
wow,
power.
I had no idea.
So
Okay.
yeah.
So these are panelized processors that 200 millimeter by 200 millimeters is what you said. Which is it
Yeah.
like um and just forgive me if I'm wrong, like TSMC, I know they're working on bigger and bigger like the CoWoS substrate packages. Is this kind of an extension of that, or is it just
Yeah,
well
it
into the
is. It
yeah,
is. I mean, the CoWoS S, CoWoS L have limits in terms of what's
yeah,
possible. There is a
yeah,
huge, as you might know, there's a huge capacity problem around
yeah,
making those substrates. Intel's got EMIB, for example.
yeah,
They're getting more and more business because people are not getting the
yeah,
CoWoS
yeah,
substrates they need or package assemblies they need to have. So and then you're moving from organic substrates to inorganic with the glass. Glass has great thermal properties. There's no question that it's going to transition to glass. And then once you're into a glass substrate, sort of the sky's the limit. I mean, I can't even 600
mm,
millimeters. That's 6/10 of a meter on a side.
yeah,
It's
yeah.
unbelievable. It's hard to imagine them being that size.
One more question. The
Sure.
glass substrate as opposed to what is being used currently, just to because I don't really know.
Yeah, it's so far as I know, it's an epoxy material, much like what we would use when we overmold our
Mm,
modules. So
mm,
it's materials that have been used time out of mind for normal semiconductor packaging. So the black
mm.
epoxy that you see, which is an
Yeah,
organic compound.
yeah,
Yeah.
gotcha.
By
Okay.
the way,
Yeah,
just one last thing.
yeah, yeah,
I think it's fascinating that you're mounting chiplets, which of course are silicon for the most part,
yeah,
maybe some gallium nitride or whatever the co-packaged optics might be, some other material. But the
yeah,
vast, memories and processors are in silicon, and of course, silicon comes in glass is also silicon based, and
yeah,
so all of a sudden you're back to almost the entire thing being silicon based, and that's of course why the TCE, the thermal cost efficient of expansion,
yeah.
works out much better than with a more of an epoxy approach for that substrate.
Right. Okay.
Yeah, it's
I'm
fascinating.
gonna have to research this in more detail, and I'm very interested in learning more. And you feel vertical power delivery solutions, as you said, are non-negotiable at that point. Um,
Absolutely not.
but it also potentially makes integrating voltage regulators maybe not as feasible.
Well, it depends on what the IVR,
Yeah,
suppliers, developers come up with. I don't know. I can't. I
yeah,
think they're staring down a really big challenge on this 2 volt.
Yeah.
I don't know. I don't know what to say. It's sort of like go talk
Yeah.
to them because I don't know how they're going to address that. I don't.
Okay.
Yeah.
Okay.
Yeah.
Gotcha.
Yeah.
Well, yeah. Thank you.
Okay.
Thank you for that
Yeah.
time.